This is Geometry Lesson 2.4. It's called Good Definitions. The big idea says good definitions are clear, accurate, short, and contain only undefined terms or terms that have already been defined. So we're going to be focusing on what makes a good definition and then looking at some specific definitions of some geometric figures or things in geometry that we need to know and define to move forward. So when we're talking about something being a good definition, there's three properties that we're going to look for. Number one, it only uses words that are either commonly understood, they were already defined, or purposely undefined, like we talked about point and line and plane. Number two, it also has to accurately describe what's being defined. I think that is pretty straightforward. That makes sense. It could use a lot of words that we know and that are defined, but if it doesn't actually describe what we're trying to define, then it's not a good definition, obviously. And then number three, and this is where, if you go back to the big idea, this is where the short comes in. We don't need a big wordy definition. Number three, it includes no more information than is necessary. And so we're going to go ahead and use these properties and do number one on the back here real quick. So if you flip your page over, number one says, why is each of these not a good definition of a midpoint? Now, I think in order to do this, we actually want to talk about what a midpoint is first. So if we go right underneath the properties here on the front, the definition of a midpoint, mid we know is in the middle. The midpoint of a segment AB is the point M on AB, where AM, this distance here, AM equals MB. Those are equal to each other. So basically what it means is it's directly in the middle. It splits this in half. If this whole distance here was 100 and this is the midpoint, it splits it perfectly in half. This is 50 and 50. Now just looking at a picture, you can't just assume that it's the midpoint. It needs to tell you that. Okay, but that's what a midpoint is. It cuts the segment in half. All right, let's go to, and that's a good definition, very straightforward. Midpoint of a segment AB is the point M on that segment where AM equals MB. Gives you all the information you need. It's very concise. Let's take a look at some bad definitions of a midpoint. So if you flip it over on number one, we're going to talk about why is each one of these not a good definition of a midpoint. So letter A. The midpoint of AB is the point between A and B. So is that true? Is the midpoint between A and B? Yes. But why is that not a good definition? So let's go back and look at our properties. Does it only use words that are commonly understood or defined? Yeah, we know what between means, right? We know it's between the two. So that's fine. It's a pretty short definition. It doesn't include anything extra that we need to know. But number two, does it accurately describe what's being defined? The midpoint of AB is the point between A and B. And I would say no, this could be anywhere. Between A and B. This definition just says it's between them. It could be anywhere. We need to make sure we know it's directly in between and cuts it in half where the two pieces are equal. All right, so this violates property number two. So if we go back and look at that property, it does not accurately describe what's being defined. It tells you something about it. It's between those 2 points, but it doesn't accurately define exactly what a midpoint is. Okay, so number two, or letter B, the midpoint is the ideal location to minimize commuting to A and B. What the heck is that even saying? Okay, so what's wrong with this one? This one is using terms that are not common or defined. It's talking about ideal location. What does that mean? To commute between A and B. What is that talking about? Commuting. We haven't defined what that means in geometry, commuting. Okay, so if you look at the properties, that violates property number 1, using only words that are commonly understood, defined earlier, or purposely undefined. Okay, so that one violates property number 2. Let's get this back in focus. All right, and then the last one. The midpoint of AB is a point on AB that makes AM equal to MB, AB equal to 2AM, and AB equal to 2MB. Well, if we really want to start examining all of that, some of that actually is probably true, if not all of that is true. But do I need to write all of that out just to define what a midpoint is? No, this is too much info. Even if it's all true, it's too much for a good definition. And so this violates number 3. It includes no more information than is necessary. This includes way too much information to be a good definition. So this violates property number 3. All right, back to the front. So we talked about the definition of a midpoint. We're also going to touch on a circle. We all know what a circle is. We could identify it, right? And I could give you something like an oval, and you'd say, no, that's not a circle. That's an oval. But how do we actually define it? So the definition of a circle and a radius, we need to know what a radius is to define the circle. So first of all, we all should know the radius is the distance from the center to the outside. And we're not going to talk about it right here, but diameter would be the distance all the way across the circle through the center. So not measuring across here, but through the center of the circle, all the way across is diameter. And then from the center to the outside to any point on that circle is your radius. So a circle is the set of all points. That's talking about all of these are a point in the set. Not just random ones out here, all of them. All points in a plane at a certain positive distance, which is the radius, from a certain point, which is its center. So this is a good definition. It's very specific. It's the set of all points on a plane, flat plane, right? This is not three-dimensional. On a flat plane, that's why we say that. That is a certain positive distance. Well, that's a little excessive. We know a distance is positive. But it's all the points that are a certain distance from the center to the outside, which is the radius. So we have this point that's the center, and we've got this certain distance. And no matter which direction I go, if it's the same distance, it's going to hit the outside. Now, I'm not an artist. That's obviously not a very good circle, but it's the same distance from the center. So it's the set of all the points that's the same distance from the center. That's a good definition of a circle. All right, and we've talked about now these conditionals and their converse. And specifically now, relating that stuff to definitions, we can write definitions as what's called a biconditional. So a biconditional is when your conditional and its converse, we've talked about those, that's just your if-then, and your converse is when the P and the Q flip. If they're both true, so we looked at it. Sometimes the converse is false, even if the conditional is true. Sometimes we give a conditional that's false and the converse is true. Sometimes they're both true, sometimes they're both false. We haven't looked at it and said this is always how it's going to be. It's different every time. But if a conditional and its converse are both true, they can be written as what's called a biconditional. So if P then Q is true, and you flip it, and Q then P is also true, you can write this special thing called a biconditional, which looks like this. The arrow points in both directions, which should make sense, right? It's true forward, it's true backwards. So this is showing you it's true both ways. But when you read it, this says if P then Q, if Q then P. If we have this biconditional going both directions, you read P if and only if Q. So it's very specific. If and only if. That's how you read the double arrow. P if and only if Q. So what it's telling you is this is true only if this is true. We could write a converse where this is true because of this sometimes, but then when I flip it with the converse, that would not always be true. So this only works if they're dependent on each other. That's a good way to think about it. This is true if and only if this is true. Okay, some examples here. If 4x equals 20, then x equals 5. That's true. If I flip that and take the converse, if x equals 5, then 4x equals 20. That's also true. So we can write the biconditional 4x equals 20 if and only if x equals 5. There's no other options, right? 4 times something else cannot give me 20. 4x equals 20 if and only if x equals 5. So this was P then Q, with P being 4x equals 20 and Q being x equals 5. Then they took the converse, Q, then P. And since both were true, we wrote this as P if and only if Q. 4x equals 20 if and only if x equals 5. Another example, if x is positive, then x is greater than negative 5. That's true. But the converse, if x is greater than negative 5, then x is positive. That's not always true. Negative 2 is greater than negative 5 and is not positive. So that's false. So a biconditional here cannot be written because when I took the converse, it's false. If you tried to write that, you would say x is positive if and only if x is greater than negative 5. Think about why that doesn't make sense. X is positive if and only if x is greater than negative 5. No, that doesn't make sense. There's other options. This is no good. As soon as the converse is false, biconditional cannot be written. And here's a good way to look at it. So we know that this A is part of B here in the Venn diagram. So if A is true, we know that B is true. But just because B is true doesn't mean A is. There's all these options out here. You cannot say if B is true, then A has to be true too, because there's all these options out here where B is true and they're not included inside A. So if we're looking at a biconditional, and if and only if they both have to be true going both ways, this is what it would look like as a Venn diagram. It's the same circle. Okay, everything that's included in A is included in B. This is A if and only if B. If one's true, the other has to be true as well. That's what a biconditional says. All right, let's flip it over and finish this out. So number 2, here's a definition. A right angle is an angle whose measure is 90 degrees. It's a good definition. We know that's true. We're going to write this as a conditional, and this is what we're really focusing on here. So this is a definition. We're going to write it in the form of a conditional, an if-then statement. Conditional is your if-then statement. We got to get used to seeing that word and knowing what it means. Writing a conditional is writing an if-then statement. And we're going to write it in this direction, the term, and then give you the characteristics. So the term that we're defining here is right angles. So we're going to write this as an if-then statement. So if an angle, gosh, my spelling and handwriting are terrible, I'm sorry. If an angle is a right angle, so my if part has talked about the term itself. Now we're going to use the then part. So this is your if, and this is your then. We're going to use the then to describe it, give it some characteristics. So if an angle is a right angle, then it measures 90 degrees. So we've taken a definition, we've written it as a conditional, an if-then statement, in the order term first, and then the characteristics. Okay, now we're going to do the same thing, but we're going to do characteristics first. That's your if, and then the term second as your then. So the characteristics is talking about the 90 degrees. So if an angle, God, I did it again, is 90 degrees, so that's describing it, then we're going to define the term. It is a right angle. Now, both of these are true. If an angle is a right angle, then it measures 90 degrees. True. We're flipped it. We're looking at the converse now. If an angle is 90 degrees, then it is a right angle. That's true. Okay, so if the conditional is true and the converse is true, we can now write the definition as a biconditional. That's another way to prove that a definition is a good definition. You can write it as a biconditional. All right, so we're going to say, now we don't use if and then here. We just say an angle is a right angle. Then you say if and only if. If and only if it is 90 degrees. That's the only way to classify a right angle is if it's 90 degrees. There's no other options. If it's 90.1, it's not a right angle. So an angle is a right angle if and only if it's 90 degrees. That is a biconditional. All right, and then real quick review and make sure we understand the actual mathematics here of a midpoint. Suppose G is the midpoint of segment TY and TY equals 20. I suggest you draw a picture. So we've got segment TY and G is the midpoint. So draw a segment and then draw a midpoint. It's going to go right in the middle. G is the midpoint of segment TY. So TY. And they tell you that TY, that whole length, TY equals 20. So find TG. Well, if this is in fact the midpoint, the definition says that TG has to equal GY. It cuts it perfectly in half to two equal pieces. So TG then has to be half of 20. It's got to be 10. GY, the other half, also needs to be 10. So we've got 10 and we've got 10 equaling 20 total because that's the midpoint. And then what is TG plus GY? Well, we know TG is 10, and we know GY is 10. So obviously they are 20 altogether. But if I was asking you to give this in terms of the labels and not the actual numbers, instead of saying that it's 20, TG plus GY, so this plus this, equals all of this, which is TY. Now we know that's 20. It's always easier to relate to the numbers, but if we're looking at the labels, TG plus GY equals TY.